What you are looking at right now is a fully interactive analytics dashboard analyzing 1 million mobile money transactions across Kenya's 47 counties. This is the Kenya Mobile Money and Agent Network Intelligence Project, built entirely from scratch using Python, MySQL, and Power BI. Let me show you what it can do before I explain how it was built. You can hover over any KPI card, that is key performance indicator, to get a deeper breakdown. Here, hovering over the success rate card shows a live breakdown of successful, failed, and reverse transactions. And with a single click, we move to the geographical intelligence page showing how revenue and agent productivity vary across every county in Kenya. In the next 10 minutes, I'm going to walk you through exactly how this was built, from the business problem through the data model, the code, the SQL analysis, and finally what data actually revealed. Let's get into it. Every analytics project should start with a real business question, not just data. Here is the context for this one. Kenya has one of the most advanced mobile money ecosystem in the world. By December 2025, the Central Bank of Kenya reported 473,536 active agents processing roughly 722 billion Kenyan shillings in transaction every single month. That's an enormous network. But here is the problem. Even as the agent network was growing, average agent commissions were falling to approximately 112,000 shillings per year as of March 2026. More agents, same commission pool. Individual agents' earnings going down. So the business question I said to answer was this: how profitable is the agent network? Where is it performing well? And where is it losing money or facing operational risk? Now I could not use real Safaricom or Airtel transaction data for a portfolio project. So I built a synthetic dataset that is statistically realistic, grounded in real Kenyan market share data from Communication Authority of Kenya. 1 million transaction, 100,000 customers, 10,000 agents across all 47 Kenyan counties for the full calendar year 2025. Let me show you how the dataset was built. Before writing a single line of Python or SQL, I designed the data model. This is a star schema, the standard dimensional modeling pattern used in enterprise business intelligence. At the center is the fact table, fact transactions, which will hold all 1 million transaction records. Surrounding it are 5-dimension tables: the DIM date, DIM agent, DIM customer, DIM provider, and DIM transaction type. And dimensional location connects through DIM agent. Because in real agent network, location context flows through the agent, not directly through the transaction. This design matters because it makes DAX calculations fast, relationships clean, and the Power BI model easy to extend. The entire schema was built in MySQL 8 with proper foreign key constraints, InnoDB engine, and composite index on agent ID and date key in the fact table to speed up the most common query patterns. 7 tables total, all created from a single SQL data definition language, the DDL script. Like we have just seen from the star schema diagram, 7 tables total, all created from a single SQL DDL script. Here is what that looks like in practice. The script creates each table in dependency order. Standalone dimension tables first, like DIM date, DIM provider, and DIM customer. Then DIM agent, which references DIM location. And finally, fact transactions, which references all 5 dimensions. Every foreign key relationship you saw in the star schema diagram is enforced at the database level, not just assumed or implied in the visualization layer. This matters because it guarantees data integrity before a single row is inserted. If a transaction references an agent that does not exist, the database will reject it. That's production grade thinking. Running this single script against MySQL creates entire database structure. That is 7 tables, 6 foreign key constants, and composite index on agent ID and date key in the fact table to speed up the most common query patterns. As you can see from the sidebar, I created this before, so I won't be running this one again. 7 tables confirmed. As you can see, the schema is alive. After creating the table is when then you can run the Python pipeline to fill these tables with real data. Now that the schema is alive, we can run the Python pipeline to fill real data in the tables. Once the schema was designed and the tables were created, I wrote a Python pipeline to generate the synthetic data. This script handles everything in the sequence, populating the dimension, transaction types, customers, agents, and finally 1 million transactions, all loaded directly into MySQL. A few things I want to highlight about how this was built properly. First, credentials are stored in a .env file and loaded at runtime. The database password is never hard-coded in the script. That's a standard practice for any production grade. Second, transactions are inserted in batches of 50,000 rows at a time. That's what makes it possible to load 1 million rows efficiently without overwhelming the database connection. Third, the transaction amounts follow a log normal distribution, meaning most transactions are small with a realistic tail of larger ones. That's how real mobile money data. And fourth, provider selection is weighted by real market share. M-Pesa at roughly 80%, Airtel at 11%, and the bank agency banking handled the remainder. Before building a single Power BI visual, I ran 10 SQL exploratory queries directly against the database. This is a step that a lot of junior analysts skip, jumping straight into visualization without first understanding what the data actually contains. This is query 6, transaction type profitability, and this is where one of the most interesting findings of the entire project emerged. Look at send money. It is one of the most highest volume transaction type of the platform, but look at where it ranks in net revenue mid-table. Now look at bank transfer. Far lower volume, but it ranks third in total profit contribution. Volume and profitability are not the same thing. That single finding from the SQL query shaped how the dashboard was designed. Instead of ranking transaction types by volume, the bar chart on the dashboard ranks them by net revenue, which tells a completely different story. That's what SQL analysis before visualization is for. Let's go back to the dashboard, and this time we'll walk through it properly. The top row shows the 9 primary KPIs, and we have a total revenue of 41.6 million. The total processing cost is 5 million. Net revenue 36 million, total transaction 9.68 billion, and the transaction count is 1 million. Revenue per active agent 3.66k. Net revenue margin is 88%. The success rate is 96%. Successful transactions are 960,000, failed 30,000, and the reversed 10,000. Average transaction value is 9.68k. The line chart shows net revenue by month, growing steadily from 2 million shillings in January to 3.78 million by December. Consistent organic growth across the simulated year. And at the bottom, a dynamic insight card that reads M-Pesa leads with 88% margin overall. That sentence updates automatically if the underlying data changes. Let's move to page 2, geographical intelligence. The county ranking table shows net revenue, agent count, and revenue per active agent for all 47 counties, sorted by net revenue with Nairobi at the top. But this scatter plot is where the most important finding lives. The x-axis is agent count per county, the y-axis is revenue per active agent. If the original hypothesis was correct, that dense urban markets like Nairobi dilute per agent economics, you'd expect to see a clear downward slope. More agents, less revenue per agent. That's not what the data shows. Revenue per agent stays broadly flat between 3,500 and 3,900 shillings, regardless of how many agents operate in a county. I reported that honestly in the project write-up rather than adjusting the analysis to fit what I expected to find. Sometimes the data tells a different story than your hypothesis. That's not a failure. That's the job. And the geographic map plots revenue bubbles across Kenya. Larger bubbles represent higher revenue counties. Nairobi and the Central Islands show the largest concentration, consistent with population density and economic activity. The region filters everything simultaneously. Table, scatter, plot, and map in one click. Let me summarize the 4 findings I consider most significant. 1. The network is highly profitable. 88% of net revenue margin on 41.6 million shillings. 2. Volume and profit diverge. Bank transfer is a low volume product that purchases well above in weight in profit. 3. No urban saturation effect was observed. And 4. Operational reliability is strong. A 90% saturation success rate across all providers and transaction types. The full project is available on my GitHub, linked in the description below. That includes the Python data generation script, the MySQL star schema, and seed data, all 15 DAX measures with descriptions, the SQL analysis queries, and a written business insight document that translates everything you've seen into strategic recommendation. If you are a recruiter or a hiring manager looking for a data analyst with end-to-end project experience, Python, SQL, dimensional modeling, Power BI, and DAX, I'd love to connect. My LinkedIn is also in the description. Thanks for watching.